Hello everyone. Previously, we have studied the greatest common divisor as well as how to compute them using the Euclidean algorithm. Yet, it is still desirable to have a more concrete algebraic relation between A, B, and their greatest common divisor GCD AB. Such will certainly give us some convenience when manipulating problems from divisibility in theory and in practice. This is actually given by the so-called Bézout identity, which we will study in this section. To this end, let a and b be arbitrary integers. The Bézout identity claims that there exist integers x and y such that ax plus by is equal to the GCD of a and b. How do we prove this? Well, to start with, let us look at a trivial case where a and b both vanish. In that case, we can take arbitrary integers x and y, and ax plus by will be equal to 0 times x plus 0y, which is surely 0. On the other hand, the right-hand side in this case becomes GCD 0 and 0, which is also 0. So we're done in this trivial case. Otherwise, let us assume that a and b are not both 0. In that case, we will investigate a special set, namely S, which consists of all the positive natural numbers of the form ax plus by, where x and y are integers. As always, we will show first that S is not empty by explicitly pointing out an element in S. More precisely, let us take x to be a and y to be b. In this setting, ax plus by becomes a times a plus b times b, which is precisely a squared plus b squared, and that is, of course, non-negative. Can it be equal to 0? Well, the only possibility that this becomes true is when a and b are both equal to 0, which is not our current assumption. Hence, we see that this term is strictly positive. That indicates that this element is indeed in S, thus S is not empty. Since S is a non-empty subset of the naturals, by the well-ordering principle, let us consider its minimum, namely U. Since the minimum is also an element in that set, we know that there exists integers, say x star and y star, such that U is equal to ax star plus by star. Now, let us show that U is precisely the greatest common divisor of A and B. There are two things to show. First, we got to show that U is a common divisor, and we can proceed by proof by contradiction. Otherwise, let us assume without loss of generality that U does not divide one of them, say A. Then, by the division algorithm, we know that there exists integers Q and R, which are the quotient and the remainder respectively, such that A is equal to UQ plus R. Typically, we should assume that R is greater than or equal to 0 and is strictly less than U. However, in this specific case, we see R cannot be 0. Otherwise, the division algorithm reads A is equal to U times Q, which contradicts our assumption that U does not divide A. We thus conclude that R is strictly greater than 0 and is strictly less than U. Next, notice that we can rewrite this equation as R is equal to A minus UQ. Recall that we have already seen U can be represented as ax star plus by star. Plugging it into this equation, we see that R is equal to A minus ax star plus by star times Q, which can be rewritten as A times 1 minus x star Q plus B times negative y star Q. Although we do not know the precise value of x star and y star at this moment, we do know that 1 minus x star Q is an integer, so is negative y star Q. Hence, we have successfully written R as A times an integer plus B times an integer. Moreover, we see already that R has to be strictly positive. Together, this implies that R is also an element in S. However, U is a minimum in S. This means U should be less than or equal to R, and that contradicts the previous conclusion that R is strictly less than U. We have hence reached a contradiction, which in turn implies that U should divide A. Similarly, U also divides B by arguing verbatim. We conclude that U is indeed a common divisor of A and B. It remains to show that U is indeed the greatest among common divisors of A and B. To this end, let D be a positive common divisor of A and B. Then by definition, D divides A and D divides B. Since D divides A, D divides A times x star. Similarly, since D divides B, D divides B y star, where recall that x star and y star are achieved in the previous representation of U. Now, together, these two implies that D divides their sum, which is ax star plus by star, which is precisely our u. Hence, we conclude that D actually divides u. But this means, by the definition of divisibility, that there exists some integer m so that u is equal to m times d. However, since d is positive, u is also positive, we see that m has to be positive as well. Hence, m is actually a positive natural number. But from there, we see that m is at least 1, which implies that u is greater than or equal to d. In other words, the integers x star and y star are the desired integers indicated in Bézout identity. This finishes the proof of the Bézout identity. In the next section, we will discuss how to find the values of x and y which satisfy the Bézout identity.